Today, I'd like to start talking about the trig functions. And rather than do what your book does, I want to begin with right triangles because I think this is easier to understand. A right triangle is a triangle that has a right angle in it, a 90-degree angle. I'll typically draw my 90-degree angle down the corner here. The longest side in the triangle is the hypotenuse. It's the side that's opposite the 90-degree angle. The other two angles in the triangle have to add up to be 90 degrees because the sum of all three angles is 180 degrees. So I'm going to think of having one of the two angles that's not the right triangle, which I'm going to call Greek letter theta here. Typically, to start with, I'll draw it down in the lower corner. The other angle here, we'll talk about that later. For right now, we're just thinking about angle theta, and we're going to define 6 new functions that depend on what theta is. The names of these functions are sine, cosine, tangent, cosecant, secant, and cotangent. We'll have abbreviations for these things very shortly. We'll call these functions sin, which we still pronounce as sine, cos, cosine, tan for tangent. CSC is our abbreviation for the cosecant, SEC is short for secant, and COT is short for cotangent. So far, we really haven't said anything unless we describe how you calculate these numbers. The side of the triangle that's as far away as you can get from angle theta is going to be called the side opposite angle theta, which I'll just call OPP for short, opposite. The longest side, as we said before, is as far away from the right angle as you can get. We're going to call that the hypotenuse, just like you do in geometry, or HYP for short. And the remaining side, the part of the angle theta that's not the hypotenuse, we'll call that the adjacent side. And what we're going to do is we're going to define the sine of theta to be opposite over hypotenuse. Cosine of theta will be adjacent over hypotenuse. Tangent of theta is going to be opposite over adjacent. And these other three functions are going to be reciprocals. If you take the reciprocal of opposite over hypotenuse, you get hypotenuse over opposite. The reciprocal of adjacent over hypotenuse is hypotenuse over adjacent. The reciprocal of opposite over adjacent is adjacent over opposite. So really, you could probably get away with just using 3 of these functions, but notation-wise, sometimes the others are convenient for us. Also, you have the Pythagorean Theorem that says the hypotenuse squared in length is the opposite squared plus the adjacent squared. So out of these 3 numbers, opposite, adjacent, and hypotenuse, if I know 2 of them, I can figure the third one out, and then I could write down trig functions for the angle that we're interested in. For example, you could have a right triangle with the shorter sides being 5 and 10. That means that the hypotenuse is going to be the square root of 125. So this number, this side of my triangle, is square root of 125 units long. Then I can write down opposite over hypotenuse to get the sine function, adjacent divided by hypotenuse to get the cosine, and opposite over adjacent to get the tangent. The cosecant, secant, and cotangent values are just the reciprocals of sine, cosine, and tangent. One thing we don't know how to get right now is what the actual angle theta is if I give some of these sides in a right triangle. Either one of the two angles that are different from the right angle have to be less than 90 degrees. And we will talk about this in a lot more detail later, but we'll just accept as a statement right now that if we restrict our attention to the angles that can be in a right triangle, there is an unambiguous way to cook up the inverse of the sine function, the inverse of the cosine function, and the inverse of the tangent function. These are so commonly used that they've built them into your calculator. It's very important that you understand, though, this is not sine of theta raised to the -1 power. This is a new function. In older books, they often used the names arcsine, arccosine, and arctangent instead, as to not get confused on that point. So here's a problem. I have a right triangle. One of the angles, theta, has opposite side 9 and adjacent side 5, and I would actually like to figure out what the angle is. Because of our definitions and the fact that I know the adjacent and opposite sides, it makes most sense for me to write down tangent of theta is opposite over adjacent, which in this case would be 9/5. The claim is that there is an inverse function to the tangent function, which is built into your calculator. So take this statement, the statement that the number tangent of theta and the number 9/5 are the same number. Feed both of those into the inverse tan function, and the results have to be the same. One of the reasons I kept harping about inverse functions was I knew that we were going to see them when we got here to the trigonometry. If you take a number, theta, and feed it through a function and take the result, tangent of theta, and feed that into the inverse of the tangent function, what you should get back is the same number that you were feeding into the tangent function in the first place. Inverse tangent of theta, if I'm telling you the truth, it ought to be theta. On the other hand, over on the other side of the equation, you have inverse tangent of 9/5. This says that the theta ought to be the arctangent of 9/5. And there's a button on your calculator for this. If you look at this row of buttons, there's sine, cosine, and tangent. Up above on the faceplate of the calculator, there is inverse sine, inverse cosine, and inverse tangent. The inverse tangent is the one that I want. So I'm going to say second, and then the tangent button. This puts up the arctan function for me. I'm going to evaluate that at 9/5. Press enter. The angle is about 60.94 degrees. And I have to warn you about something here. In the mode setting, make sure that it's degrees that's selected and not that other word. We don't know about that other word yet. We will pretty soon. But for now, make sure your calculator is set in degree mode. Given the fact that I know the lengths of the side opposite and adjacent to angle theta, it makes most sense to use the tangent function here and then the inverse tangent to get rid of it. If for some reason I thought it was nicer to use one of the other functions, I'll need to know how long the hypotenuse is. The square of the hypotenuse is 5 squared plus 9 squared. The hypotenuse itself is square root of 106. This tells me that cosine of theta is adjacent 5 divided by the length of the hypotenuse, which is square root of 106. By the same reasoning as before, assuming that I'm not lying to you about these inverse functions, hit both sides of that equation with the arc cosine function, the inverse of the cosine function, and theta should be the inverse cosine of 5 divided by 106. So we'll calculate that. We'll calculate the inverse cosine of 5 divided by the square root of 106. And we get the same answer that we got before. Also, I could write sine of theta equals opposite divided by hypotenuse. That would be 9 divided by square root of 106. Take that formula, hit both sides of it with the inverse of the sine function, and you'll find out that theta is the arc sine of 9 divided by 106. Second, sine puts the inverse sine up. 9 divided by square root 106. And once again, we get the same angle back. We have to get that angle back again because the angles in a triangle are whatever they are. They can't change depending on how I'm doing the calculations. It's traditional to calculate the height of a building. So we'll say you've got some building and its vertical height is h. And you don't know what the h is, that's the problem. You march off a distance 200 feet horizontally from the base of the building, and from ground level, the angle between horizontal and the line of sight to the top of the building is measured to be 37 degrees. And our problem, of course, is what is the value of h? If you look at the picture, you know an angle, 37 degrees, you know the distance adjacent to that angle. You don't know the vertical, the opposite height, but you do know the tangent of 37 degrees is the opposite over adjacent. So tangent of 37 degrees is h divided by 200. Now notice this isn't inverse tangent, it's tangent. This was the definition of the tangent function. Multiply through by 200, and you find out that h is 200 times tangent of 37 degrees. Which works out to be about 150.71 feet. So this kind of problem, calculate the height of buildings problem. The way this is set up, it practically yells, calculate tangent of 37 degrees at you. And then once you've done that, you can easily get the height of the building. When we say that two angles are complementary, if when you measure them in degrees and add their measures up, you get 90 degrees. Of course, in any triangle, the angles have to add up to 180 degrees. So as we were saying previously, if you have a right triangle and you calculate this angle plus this angle plus that one, it's theta plus phi plus 90. That's supposed to come up 180 degrees. Subtract 90 from both sides, and you find out that theta plus phi is 90 degrees. So in a right triangle, the two angles that are not the right angle are complementary angles to each other. This is going to be the origin of the CO in front of some of our trig functions. To keep from getting confused about which side is opposite or adjacent to which angle, I'm just going to make up letters for the sides of my triangle. I'll call the lengths A, B, and C, A, B, and C. This angle is theta. The other angle we've seen has to add up with theta to give you 90 degrees. That means that the other angle must be 90 minus theta degrees. I want to calculate the cosine of theta. That's the side adjacent to theta divided by the hypotenuse. So that would be A over C. Calculate the sine of theta. That would be the side opposite theta divided by the hypotenuse. That would be beta divided by C. And tangent of theta, you look at the side that's opposite angle theta and divide it by the side that's adjacent, which using these letters would be B over A. The connection is this. Let's calculate the cosine of the other angle. That's going to be the side adjacent to that angle, that would be B, divided by the hypotenuse. So cosine of 90 degrees minus theta is B divided by C. Sine of 90 minus theta is the length of the side of the triangle opposite 90 degrees minus theta divided by the hypotenuse. That would be A divided by C. If you calculate the tangent, I've got to take the side opposite the 90 minus theta, that would be A, and divide it by the side adjacent, which is B, and we will get A over B. The cotangent is the reciprocal of the tangent, so I can just write down cotangent of 90 minus theta is B over A, the reciprocal of A over B. The sine of an angle is the cosine of the complementary angle. The cosine of an angle is the sine of its complementary angle, and the tangent of an angle is the cotangent of the complementary angle. This is why we give these three functions cosine, cosecant, and cotangent the names that we do. Even here at the beginning, we can begin to see some stuff. In a right triangle, the long side squared is the sum of the lengths of the other two sides squared. In this picture, cosine of theta is A over C, and sine of theta is B over C. If you were to calculate cosine squared of theta plus sine squared of theta, after doing the arithmetic to add the fractions together, and using the fact that A squared plus B squared is C squared, you would get C squared divided by C squared, which is 1, regardless of what angle theta is. So here's what we know about this so far. Cosine squared of theta plus sine squared of theta is 1. We know that for sure for the angles that are in right triangles, and eventually we will find out that it's always true. But at this time, we don't know about trig functions that are bigger than 90 degrees, for instance. We'll fix that up later. From this first fact, from cosine squared theta plus sine squared theta equals 1, if you divide through by cosine squared of theta, you'll get 1 in the first term plus sine squared of theta over cosine squared of theta equals 1 over cosine squared theta, which is the square of 1 over cosine theta. 1 over cosine theta is the secant of theta, and if you simplify the fractions, you find out that the thing you're squaring and adding to the 1 on the left-hand side is actually tangent squared of theta. So if you take this fact, which is true because of the Pythagorean theorem, and divide through by cosine squared theta and simplify, you find out that another fact is true as well. 1 plus tangent squared of theta is always the same thing as secant squared of theta, at least for angles in a right triangle. That's all we know about right now. If you take the first and second calculus course, this fact will be extremely convenient for you at times. Starting with your basic formula again, cosine squared of theta plus sine squared of theta is 1. This time divide through by sine squared of theta, and after all the simplifications, you'll find out that 1 plus cotangent squared of theta is cosecant squared of theta. And in math 1910 and 1920, this will be very useful for you in certain integration problems, which is why we mention it at this early stage of the game. If you're not actually going to take the calculus courses, well, we'll just have to suffer through this. This is our introduction to the trig functions. In what follows, we'll take these same ideas, except we'll remove the requirement that the angle has to be between 0 and 90 degrees. Look over these materials that I've got here. Make sure you understand what I'm talking about. And if there's anything that's not clear, feel free to ask questions about it. Next time, trig functions of any angle.